auto mechatronics, etc. See, as far as in this mechatronics is concerned, so if I try to go to my history, okay, so we all know about this industry revolution. So, as far as industry revolution is concerned, like you have industry revolution 1, industry revolution 2, industry revolution 3. Now we are marching towards industry revolution 4. So, which we call it as industry 4.0 or smart manufacturing, etc. So this industry revolution also has a key focus towards progressing this mechatronic system design. Like, in fact, I should say, like currently how your corona mutates, similar to this, mechatronics has also mutated with respect to the different industry revolutions which have come up through. Okay. So, in fact, when we just talk about the first industrial revolution, so first industrial revolution was towards mechanization, towards water and steam power, etc. Where we had quite a good amount of resources towards water and steam, and we were just moving into the mechanization. In fact, this is the first part where an automation started coming into the picture. So automation's seed was sown during the first industrial revolution because of the demand. Slowly, the industrial revolution started taking up its shape with respect to mass production, with respect to assembly lines, where we had an abundant amount of electricity. So in all these cases, if you try to look into it, so here I had steam as my water and steam as my resource. So with respect to water and steam as my resource, I was having my mechanization as my key output. Second, in the case of mass production is concerned, so I had electricity on an abundance because I was already working on generating sufficient amount of electricity, which based on the demand, I was converting the electricity towards mass production. Okay. Third generation is something related to this computers and automation. So where computers and automation started taking up a major role, where the term mechatronics started coining. So as far as in this mechatronics is concerned, so where mechanical and electrical engineering and information technology started plunging into it, where the concept of computers and automation came into picture. And with respect to automation, so slowly the mechatronics also started getting mutated, and it was moving towards the different horizons based on the applications. And now we are moving towards an area where from the adoption of computer and automation, so the mechatronics started spreading its hands towards the different disciplines such as computers engineering, electronics engineering, mechanical engineering, and then it also started looking into some of the allied areas such as industrial engineering, materials engineering, and chemical engineering. So this is where exactly this mechatronics has taken up a shape with respect to an industry 4.0 requirement. So in all these cases, there is always a myth which says that as and when mechanization or as and when technology starts developing, so it may lead to unemployment. But actually, on a technology perspective point of view, if I would like to say, so there is an increase in technology, or there is a mutation in technology because there is a requirement of demand. Okay, like for example, today in this pandemic situation, consider that if we don't have internet resource with us. So currently internet resource is pretty abundant. So that is why it is easy for us to communicate among ourselves in any modes. Today we are conducting most of the lectures with IoT. But during the inauguration, many experts have coined about this. Okay, so with respect to an advance in technology, so it is trying to cater, or it is trying to take care of the demand with respect to the current environment. Okay, in fact, when the pandemic started in the last March, so one of the industry which was taking care of car manufacturing or automobile manufacturing, they told very clearly that we can directly switch to ventilator manufacturing. This shows their efficiency, or this shows their flexibility, where they might have implemented an industry 4.0 environment so that they can easily switch on to your production. Okay. Now, as far as in this mechatronics is concerned, so this is what, so as we were mentioning about the different mutation of mechatronics, so this is what the key application which basically currently mechatronics is looking at. One is with respect to manufacturing, another is with respect to consumable products, next is with respect to defense system, and then we have a medical domain where quite a good amount of applications are coming up. So suddenly we are talking about 3D printing aspects, we are talking about imaging aspects, we are talking about smart diagnostics, nestings, etc. So these are some of the key areas where mechatronics have played a major. So we also have other set of domains such as manufacturing, material processing, automotive, and aerospace, etc. In all these domains, so there are various subdomains which are available. So one of the key areas in this is like if I try to keep a common pool as mechatronics, you have different subdomains which are there. So these subdomains are controls, electronic systems, mechanical systems, and computer systems. So each control systems, you have control electronics, and then you have a mechanical CAD. Okay. Now, as far as in this, so these are some of the outcomes of the development of mechatronics. Okay, so like one example I would say is a kind of automated cushioning which is available. So the main objective of this automated cushion is that it will not only sense your ergonomics, it can be also used for powering it. Okay, so here if I try to look into the whole domain of elements which are available, and these complete domains are well integrated. So one, it might be a system which has a direct interaction with human, and this is a kind of a robotics. So obviously robotics is a subset of mechatronics system where we are talking about an intelligent robotic system which plays a major role in today's environment. Then we have a smoke detector. Basically, a smoke detector is a simple example of a mechatronic system where you have an actuator and a sensor in place, which is mainly makes it intelligent towards the application. This is a kind of an intelligent prosthetic system, so which is available. So this intelligent prosthetic system is slightly an advanced version of the unit. So as well as in this intelligent prosthetic system, like you are trying to capture the brain signal, and with respect to your brain signal, you are trying to control your actuators and sensors based on your requirement. And so this is one such example where we call it as biomechatronics. So where a wide varieties of activities are happening today. In fact, people are attempting towards prosthetic. People are attempting towards developing small micro robots for diagnosing as well as for some kind of micro treatments, etc. And then, if I try to talk about the next domain, so it is an automobile sector, which we call it as an autotronic system. So in this autotronic system, so again you have a kind of area where you have wide varieties of sensors which are available. So these sensors are well integrated into this autotronic system, and through this you can go for a self-diagnosed vehicle or an automatically guided vehicle, etc. And this high-speed trains are another area. Basically, we call it as mass transfer or mass transportation. So this is one of the key area where most of the governments are looking into. So currently, you might have seen various kinds of mass transformation systems which are available. So these mass transformation systems also takes a phase with respect to the amount of technology which is available in front of you, and based on that, how it moves. Okay. So in this lecture, I would like to discuss about one of the key aspects. So like I would say that the main motto of this lecture, you have wide varieties of mechatronic system in and around you. But as a faculty, so we should have an expertise in discretizing the different elements of a mechatronic system, as well as how to identify the sectors or how to make it in the form of a block diagram for our understanding. Okay, so basically it's our duty to teach the students about the different functionalities of mechatronic system. Right. So in this lecture, I would like to give you a kind of an expertise to you, so that whenever you see a mechatronic system, you should be able to identify what are the different components involved. So as far as if I try to talk about a definition of mechatronics, so in the case of mechatronics, basically it's a synergetic combinations of precision mechanical engineering.
Excuse me, sir, your slides are not moving.
Acha, okay. Actually, I am just in the whiteboard now. I will just.
Yeah, it was not showing.
1 minute on. I think I will go for screen one so that it becomes clear. Okay, so is my whiteboard visible?
Yeah, it is now it is changed.
Okay, okay. So as far as in this mechatronics is concerned, so if you try to define mechatronics, because as I had mentioned earlier, so it gets mutated with respect to your different applications. So we need to put up a common thread so that with respect to that thread, we should be able to map our system about the mechatronics availabilities. So it is a synergetic combinations of precision mechanical engineering, the electronics control, and the system thinking. So when I try to talk about the system thinking, so it is something like there is where exactly your sensors plays a major role. So from your sensors, you are trying to capture the data, and with respect to that, your system behavior gets changed or it gets integrated. Okay. So as far as there are wide varieties of drawings which are available to predict your or to expose your mechatronic systems, so which we call it as integration. So as far as integration is concerned, so we have the mechanical, we have the metallurgical, and then we have the electronic sciences. Okay, so but in all these cases, so one important aspect, so which I have emphasized about the mutation of mechatronics. So this mutation of mechatronics is basically taken care with respect to the information which is getting progressed. Okay, so your information plays a major role. So how your information is being taken up, so based on that, the mechatronics also takes its shape for different applications. So like for example, let me just give you a simple example. So we all know a washing machine uh, is an example of a mechatronic system. So in the case of washing machine, so let me just explain the working of a washing machine in the form of a block diagram. Okay. So in the case of washing machine, you have a mechanical device. So this mechanical device is the washing machine drum, which you see. From this washing machine drum, you have an actuator. So the main function of this actuator, so we all know what is an actuator. So whichever which gives a displacement, we call it as an actuator. Like for example, when I try to give a kind of input to it, so based on that, it gets displaced. So let me just give you a general overview about the different types of actuator in due course of time. So this is your pump. Then there will be a valve which will be available. Then we have a heater in place. Then we have the motor in place. Okay, and then this is your actuator. And then as far as your sensor is concerned, you have a door closer sensor. Then you have your water temperature sensor. Then we have our water level sensor. And then you have your motor speed sensor. Okay, so this is your washing machine front where I am discretizing into two. One is your actuators and another one is your sensors. Now I have a control unit in place. Okay, and then I have my communication in place. So in the case of communication, so I have my clock input. Then I have my program. Then I have my selector button. Then we have the wash cycle display. Okay, so in this case, so if I try to look into the interfacing aspects point of view, so this is your communication, which is nothing but your front panel, which is available. So this you have your clock input and your program, which is under your purview. Then you have your selector button over here. Okay, so which is being fed into the controller. So from the controller, you are connecting, the controller is interfacing with your actuator, which is available over here, so that the actuator starts actuating, which is nothing but displacing. In the case of washing machine is concerned, your electrical inputs are being converted in the form of a rotary displacement. Okay, so this rotary displacement is directly fed into the washing machine drum. Okay, so this is how your communication is happening. So from this communication, so there is a sensors which are available. So these sensors are interfaced. So either it might be a door lock, or it might be a water temperature, or it might be your water level, or it might be your motor speed. And from this sensory inputs are fed back to the control unit as shown over here. Okay, so this is a kind of, so from this control unit, again, you are interfacing with your water cycle display. Okay, in the current scenario, so these systems are made it in such a way that instead of your water cycle display, so you have an LDS sensor. Basically, this LDS sensor is a laser-based sensor which will try to measure the turbidity. So once the turbidity is low, then automatically it will give an input back to the system, and then again your system works. Okay, so system works. Okay, so now this is an overall generic idea about how a mechatronic system works. Basically, it might be a bit preliminary, but still, it's my duty to bring you on board. Okay, now with this as an idea, now let us make a generic system, and what are the different types of generic systems available, and how these generic systems work. So as far as in this generic system is concerned, so in fact, these are called as mechatronics. These are called as mechatronics architectures. So as far as in this mechatronics architecture is concerned, so I have a actuator. Then I have a sensor. Then I have an input signal conditioning and interfacing. Then I have a user interface. Then I have my digital control interface. And then we have our output signal conditioning interface. Okay, so this is the overall structure of a mechatronic system. So any mechatronic system you take an advanced level, or you can take a primitive mechatronic system. According to us, the primitive mechatronic system is a bimetallic switch. Okay, so either any of these systems, if you take this kind of some architectures will be available, so that it is easy for you to pick up your block diagram form. So, understanding or designing the block diagram will be the key motivation for you to study any kind of mechatronic system. Okay, so what I'm trying to do is, so this is my mechatronics, this is my mechanical system, I should say. So under this mechanical system, I have my actuator and my sensor. Then you have an input signal conditioning. You have a digital interface. So if I try to look into the overall workflow, my overall workflow goes like this. And then I have my digital control interface. This digital control interface has a handshaking mode with the user interface. And then we have the output signal conditional interface. Okay, now let us go one by one about the different mechatronics architecture. So first, let us talk about this actuator. What do you mean by actuator? So as far as this actuator is concerned, so people might have heard about this actuator. So when you try to coin the word actuator, so immediately one important actuator which comes into your mind is a motor. Okay, so in fact that is what we have seen during this washing machine application also. Okay, so actuator in a simple term, in a crude term, if I would like to say, any system which gives me an displacement as my output, I call it as an actuator. Now, based on my different domain, these actuators are classified. Like in the case of mechanical, you have the CAM systems. Like I can just classify based on the different domain. So with respect to mechanical, we have the CAMs. We have the engines, etc. In the case of electrical domain, so basically in the case of electrical domain, we have the solenoids, which are available. In the case of electromechanical domain, we would be having the motors. The motors are considered as electromechanical domain because it has both mechanical as well as electrical aspects coming into the picture. Okay. The most important actuator which is widely used for different applications, which comes under the category of hydraulic and pneumatic systems. So as far as these hydraulic and pneumatic systems are concerned, so where it is something like you use a compressed fluid for getting a displacement, like you might have heard about cylinders. So in the case of cylinders, there are different wide varieties of cylinders which are available, where a double acting, cylinder, single acting, etc. So where you apply, so this is the overall construction, or I would say an elementary level of pneumatic system. Like when I try to pass an air through it, this will move in this direction. And similarly for a return stroke, I can just pass an air through it. Okay, or even sometimes you can use a compressed fluid form. So based on your load or based on your capability, so you can just select this actuator. So the most important other kind of actuator which are in place are called as smart actuators. So these smart actuators are pretty, I would say, interesting actuators. So these actuators are material-based actuators. So these materials gets displaced with respect to a different actuation. In fact, so we will be discussing about this in the post-lunch section. So some examples such as shape memory alloy-based actuators, so most of you might be aware about piezoelectric actuators. Okay, so there are some certain amounts of hydrogels which are available, so which we will be discussing. Now, when we talk about actuators, I think you might have got a clarity about what do you mean by an actuator. Now let us discuss about sensors. So as far as sensor is concerned, so a sensor is nothing but basically it will be having a sensing element. So based on your application, so this sensing element will work upon. Okay, so there are wide varieties of sensors which are available, which most of you might be aware about it, like strain gauges. We have the thermocouples. Then we have accelerometers. Then we have potentiometers. We have digital encoders. So again, when you try to classify your sensors, so your sensors are classified based on your sensing element, and then based on your transduction element. So as far as your sensing element is concerned, so it depends upon your application where you are going for. For example, like in some cases, it is very difficult for us to keep a contact-based sensor. So in those conditions, we may go for a non-contact type. Like for let me just give you a simple example. So I have a plate. I'm just heating the plate. So one option we all know, common to know about it, is using a thermocouple in it. So you can just immerse a thermocouple. From the thermocouple, you can get the temperature. Other option would be kind of a pyrometers, thermal imaging cameras, etc. So these are quite interesting systems which works on the non-contact based environment. So using this non-contact based environment, you can stay. Okay. So where optics plays a major role. So that is where exactly this optomechatronics comes into picture. So I'll just give you a brief overview about this application of this optomechatronics. Okay. So next concept. So in this sensors, you have wide varieties of sensors which are available. So even your MEMS based sensors have a key area in this particular domain. Okay. Now let us talk about this input and signal conditioning interface. So as far as in this input and the signal conditioning interface is concerned, we have the discrete circuits, which includes filters, amplifiers, AD, analog to digital converter, etc. In the case of output signal conditioning unit is concerned, again, we have some kind of power transistors. Then we have power amplifiers, etc. Then you have a digital control interface. So as far as in this digital control interface, one of the key element is your PLC, which we called as programmable logic controller. So as an extended version of this, we have a SCADA system. Then we have which takes care of the entire plant. Okay. So as far as your user interface is concerned, so in this user interface, you have two different key domains. One domain is your input interface, and the other domain is your output interface. So as far as input interface is concerned, we have the keypad, joystick. Nowadays we are with microphone, touch screen, etc. In the case of output interface, we have the LEDs, digital displays, LCDs, monitors, buzzer or speakers, etc. So some of these are called as the key aspect of a mechatronic system. So this is an overall architecture of a mechatronic system. Now we go back to some of the applications of these. So now you might have got a clarity about the different architecture of mechatronic systems. Now we will take an example which most of us are fascinated. It is called as an engine management system. So as far as an engine management system is concerned, so again, you can just discretize your unit in terms of microcontrollers, and then you have your system called as multi-cylinder engine with 4-stroke petrol. Okay. So we have the spark timing. Then we have the air fuel mixture solenoid. We have the fuel injection valve. Then we have the engine speed. Then we have the crankshaft position. We have the spark timing feedback. We have the engine temperature. The throttle position and the mass air flow. Okay, so each has its own levels of communication. So in the case of spark timing, in the case of air fuel mixture solenoid, and in the case of fuel injection valve, you have a communication from the microcontroller to the cylinder, which is nothing but your actuator. And in the case of the engine speed control from the actuator, so it is being sensed and it is being fed into the microcontroller. Similarly, in the case of crankshaft positions and in the case of spark timing. And this is with respect to your engine temperature, which also act as a sensory system for your microcontroller environment. And you have your throttle position, where again the communication flows to the microcontroller, and your mass current flow, mass airflow. Okay, so this is to give you a clarity that whichever system you take, so you can just discretize the system based on the requirement and then you work on. So now, when we try to go into the some of the important aspects with respect to a building block of these mechatronic system is concerned, so on an advanced level. So we were discussing about one of the important aspect, that is an information. So how the information is processed, and based on that, how do we try to prepare our building block? So in that aspect, if you try to look into it, so I have one domain, which is nothing but the world, which has a cloud or a data which is available with me. Then I have my environment module. So this we call it as building blocks of okay. So hope you could be able to see my screen. Building blocks of mechatronic systems. So you have an interface module over here. We have a processor module over here. Then we have the software module over here. Then we have the communication modules. We have the actuation modules. We have the measurements modules, which is nothing but this, which acts as a key element for sensing applications. And then we have the assembly module. That is from the environment to the assembly. Okay, so where you have your handshaking modes which is there. So let us make the flow in this particular direction. So from the assembly mode, it goes to the measurement module. From the measurement module to the communication to the processor. So this is an handshaking region, which is a handshaking happening between the processor module and the interface module. And this is with respect to world. Then again, you have your communication module, you have your actuation module, and from your actuation module, you have your assembly line. Okay, so this is the overall building blocks of the overall structure of the mechatronic system. Okay. Now, so in this environment, one of the key aspects which we need to look into it, how we need to balance our system. So normally, in order to balance our system, it is always required that we need to have a modeling and an analysis and a hardware implementation skills. So this will give us a better orientation that how our overall system will behave. So basically, in a nutshell, if I would like to say, so first you need to have a modeling skill. With respect to your modeling skill, you need to appropriately convert it to your analysis skill, and from their analysis skill, it will be a implementation or the interpretation skill. Like I also understand after my talk, there is a talk by Dr. Vasu on modeling analysis. So this is a overall balance. If I try to look into this, there is a need to be a balance in the mechatronic system. So in this mechatronic system, so basically, like I have a model parameter identification, which is one terminology. With respect to my model parameter identification, I can have two decisions. One decision is with respect to measurement, calculation, and specification. The other one is which parameter to identify what rest are performed. Okay, so this is now connected to my physical system. Then we have our physical model. Then we have our mathematical model. Okay. So in the case of physical system, so we will be looking into some of the assumptions and engineering judgments. In the case of physical mode, your physical laws come into picture. So as far as your physical law is concerned, so we will be considering the different domains. Like for example, so I am taking an example of a bio-related biomechatronics. For let us consider a pacemaker. Okay, so I am thinking about designing a pacemaker. So obviously, in the case of pacemaker is concerned, I need to consider the fluid flow. I need to consider the material interaction, basically the solid mechanics related aspects, and I also need to consider about the factors. So here, so when I try to talk about the physical laws, so you are trying to integrate different domains like such as solid mechanics, electronics, and fluid mechanics, so that so you need to look into the fundamentals of this, and based on that you will be modeling your device. Okay, now this is the first level kind of model. So the next level is something related to the actual dynamic behavior. So as far as your actual dynamic behavior is concerned, so we have the experimental analysis. And then, so since I have my actual dynamic behavior, so I need to use a comparator over here to the predictive dynamic behavior. We have the engineering solutions over here. So from these engineering solutions, you are fixed up to your comparator. And then we are trying to move into the decision-making concepts. Design decision, where your model adequate and your performance are compared. Similarly, we have a design complete over here, where we are trying to compare the system, and from these decisions, again, it is moved to the physical ones. So this is the overall, what I would say, a background architecture. So basically, a designer needs to take it into consideration before designing any kind of mechatronic system. Okay. So hope I have given you some kind of insight about how to design a block diagram for, or how to identify your different components of your mechatronic system and how to integrate it in terms of block diagram. Okay, so I think I understand that there are some questions are there. So we just check these questions and then go. Could you see the flow chart? Okay. Okay. Is there any questions? So you can just type the questions in the chat box so that then and there we can address it. Okay. Now, one of the important aspect which I would like to explain over here is like we were talking about this mechatronics getting mutated, okay, with respect to different applications. So based on the current scenario, these mechatronics are basically being classified into different levels. Okay, in fact, the different types of mechatronics are available. Okay, so one mechatronic system, one type of classification is called as autotronics. So as far as autotronics is concerned, where you have currently, this is one of the key area where people are working upon, where in fact, I think I have a slide on it. So this is how your autotronic system basically moves. So in this autotronic system, so we have a board level system, we have a vehicle level system, and we have a traffic management level system. So based on that, you have a complete technological advancement which is being translated to different levels. So one is something related to your powertrain and your engine management. So another one is with respect to your vehicle stability as well as your steer-by-wire arrangement. And another one is with respect to your intelligent transport system. So as far as autotronics is concerned, again, in the case of autotronics, you have the actuators which comes into your picture. Then we have the sensors which comes into the picture. We have the control systems which comes into the picture. Then data communications. Data communications. Most important is your diagnostics. Okay. Today, many of these cars are coming up with this diagnostic system. In fact, currently cars are coming up in such a way that it will give, when you switch on your car, it will give you, it will check all the sensory activities available in the car, and it will be transferred to your app to show is there any fault in any of the sensory systems. In case if it is going to fail, it predicts it and it gives you an understanding at which point it is going to fail. So that is one of the key advanced level of an autotronic system. Okay. So the next system which I would like to talk about is the next classification is optomechatronics. So as far as optomechatronics is concerned, so it is something like where a light is used for any kind of actuation. So in fact, it started with an advancement of a laser. So when laser started taking up a shape or controlling or making a monochromatic light source, it started taking up a shape. So automatically the light are used for actuations as well as sensing applications. Like one example, I would say the last to last year there was a Nobel Prize was given to laser tweezers. That is, these laser tweezers has a capability to handle cells. Okay, in fact, in our optomechatronics session, we will be discussing about it. So this optomechatronics is one of the key area where, you might have heard about intelligent mirrors. Okay, so these intelligent mirrors are capable enough, or I would say it is flexible enough in such a way that when you try to actuate it, it gets deflect. From the deflection, you could see, or you can just orient your overall light intensity as well as your light reflection coming out of it. Like in DRDO, so there is an element which we call it a seeker. So the main objective of the seeker is to align your missile based on the lead. Okay, so what it does is it has a kind of an intelligent system, intelligent mirror, which is available. So these intelligent mirror basically deflects based on the feed which they get from it, and from that you can try to orient your laser for a destruction purpose. Okay, so these are some of the advanced level of optomechatronic systems which are being available for the current day. Okay, so the next one which I would like to talk about is called as a micromechatronics, or in other words, we call it as MEMS. Okay, so which we will be discussing in detail in the upcoming slides. Okay, the last one, or I would say the most advanced and the intelligent one, which we call it as adaptronics. So this adaptronics is something, one of the key area which currently researchers are focusing upon. So it has its own advantage. In fact, if you could able to see my slide. So in this slide, so this is an integration of complete technologies as well as a complete communication which is being taken up into our picture. So as far as in this adaptronics is concerned, so you have a complete intelligence is being integrated. So the main objective of this intelligence is, so based on your requirement, your sensor and your actuator will take up a different shape, and based on that it tries to behave. So this is one important aspect with respect to an adaptronic system. So as far as an adaptronic system, your haptic device plays a major role, which acts as a major aspect for taking care of your input and your output level, output based systems. Okay, so as far as in this case is concerned, so your adaptronics has been employed in different space applications, in different DRDO applications, as well as in different defense applications, in different medical applications, etc., which is slowly picking up its pace because of the advancement in information system. Okay. Now let us move into this micromechatronics, or I would say a MEMS. Okay, so as far as MEMS is concerned, so we all know it is called as micro electromechanical systems. So before going into this, I would like to show you a small video about a MEMS system. Okay, so it's an open source video. Could you able to see my screen?
Yeah, yes, sir. It is visible, sir.
Okay, okay. Hope I think the sound might not be there.
Yeah, while sharing, you have to make it as optimal sharing like that. Then it will come, sir. Once you stop the sharing, once you are sharing the screen, no, right top right, you will have one option will come, sir. That is, you make it as optimal for video and audio. That second option, you click it.
Automatically optimize for motion
next,
and
yeah. The second one. If you type, okay.
Okay, so now I think it should be.
Now you can. It is coming, sir. Now.
Audio is coming, right? Okay.
Look closely and you will see them.
So
Tiny machines, nearly invisible to the human eye.
Will give you an
These micro machines make automobiles safer, insulin pumps for diabetics more accurate, and hearing aids more efficient. MEMS, or micro-electro-mechanical systems, describes both a category of devices and the technique for manufacturing them. These tiny devices have elements ranging in size from 1 to 100 micron, about the thickness of a human hair. MEMS devices are generally divided into two categories: sensors and actuators. Sensor devices gather information from their surroundings, and actuators execute given commands or act generally through highly controlled movements. MEMS are made using the basic fabrication techniques and materials of microelectronics. Thin layers of materials are deposited onto a base and then are selectively etched away, leaving a microscopic three-dimensional structure. In this way, MEMS processes construct mechanical as well as electrical components. The electrical elements on the chip process data, while the mechanical elements act in response to that data. Hence, a complete system on a chip. Integrated circuitry provides the thinking part of the system, while the MEMS component complements this intelligence with active perception and control functions. Known as MST, or Microsystems Technology, in Europe and Asia, the potential for MEMS technology is endless. MEMS devices are already used in an extensive range of products. They can be produced in large quantities with proven fabrication techniques. For example, crash sensors for airbag safety systems are actually MEMS devices that measure the force of an automobile crash and deploy an airbag if the force is great enough. Also, with the help of MEMS printheads, inkjet printers have developed from crude, slow black and white devices to fast, flexible photographic quality imagers. And thanks to MEMS digital micro mirrors that control light, video projectors in offices around the world are now able to produce razor-sharp, bright, colorful images. MEMS technology has become so widespread since its beginnings in the 1980s that it is estimated that there are now between 15 to 20 MEMS devices for every person living in North America. There are two common examples of MEMS improving existing technology: the automotive crash sensor and the digital micro-mirror device. A key element of modern automotive airbag systems is the MEMS crash sensor, known as a MEMS accelerometer. These sensors are more effective than earlier systems, meeting more stringent safety standards. The core of the MEMS accelerometer is a central mass that moves in response to a vehicle's acceleration. This inertial mass is mounted on a hinge or spring that limits its movement and returns it to a central position when at rest. Sensitive electrical sensors in the chip read the mass's movement and relay this data to a connected microprocessor. The microprocessor monitors the state of the accelerometer at rest and in motion. In a collision, there is a sudden change in acceleration. When this change reaches an unsafe level, the airbags are deployed. The entire process takes only a fraction of a second and has saved millions of lives. MEMS technology allows crash sensors to be built from one or two simple chips. Earlier systems needed many electrical and mechanical components located throughout an automobile for measuring the same data. Reducing the number of components increases the accuracy and lowers the cost of these systems. The MEMS micromirror device, or DMD chip, is used in modern video projectors, home theater systems, and televisions. This chip uses microscopic moving mirrors to improve the image quality and overall reliability of these products. The micromirror device is, in its simplest form, a light switch made of millions of hinge-mounted mirrors. Each mirror measures about 1/5 the width of a human hair and corresponds to one dot or pixel in a projected image. Mirrors are mounted on tiny hinges that enable them to tilt either toward the light source to reflect light or away from it to block the light. This creates a light or dark point on the projection surface. The length of time the mirror faces the light determines the brightness of each dot. In color systems, projectors can create over 16 million shades of color. These systems are producing such high-quality images that they are now being installed in movie theaters, replacing film projectors. MEMS technology will continue to quietly improve life as we move into the future. We may not be able to see the devices, but we will see its applications as they continue to affect our lives. Because MEMS is a flexible technology, it has the unique ability to improve current products, delivering new levels of performance and efficiency to both mass market and highly specialized applications. In the computer market, MEMS is revolutionizing mass data storage by miniaturizing components for disk drives, servers, and peripherals, meeting the increasing needs for low-cost, high-capacity digital storage. In the consumer electronics market, acoustic MEMS chips are changing the way sound reaches our ears through cell phones, personal stereos, and hearing aids, providing less distortion and higher quality and clarity of sound. MEMS technology is meeting its potential for greater commercial use in several fields of technology. In addition, MEMS size and integration allow for whole new classes of products that would never have been possible with conventional approaches. In medicine, the advent of MEMS chips for drug delivery can benefit any patient who must follow a regimen for medication, as a single chip embedded in a patient can release the correct amount of drug over a given period of time. Also, MEMS sensors embedded in scalpels allow surgeons to measure the force and depth of their delicate incisions. The industrial market will see MEMS chips that detect gas leaks and other pathogen agents, keeping the workplace safe. MEMS technology is everywhere. It has become an inevitable part of the path to more effective and diverse products at the consumer level and beyond, and has already improved our quality of life. Products with MEMS devices perform better, respond faster, and are more reliable. They improve current products in ways that are not possible with traditional electronics. The beauty of MEMS technology is that it is used in hundreds of products today, making it the technology of the present, but has the proven potential to be in millions more products in the future, thus securing its role as the technology of tomorrow. MEMS.
Okay. So with this video, so you might have got an idea about what do you mean by MEMS system. Okay. So in fact, if this pandemic would not have been then, we would have taken you to our laboratory. So we also deal with some kind of MEMS-based devices. Okay. Now let us come back to this MEMS-based structure. So how? So the main objective of this particular point is when you see a MEMS-based structure, how do you explore the MEMS-based structure and how do you come up in the form of a block diagram? So for that, I would like to give you a brief overview about how does the MEMS structures, what are the different elements of MEMS structures and how on an explorer view in the form of a block diagram, it can be interpreted. Okay, so like when we talk about these MEMS, I just bring it down in a small area where we have the signal transduction and processing unit. So I'm writing in a in the whiteboard now. Hope you could able to see. Okay, so, processing unit, and then we have the actuator, and then we have our sensor. So this is as a overall. So it works on the handshaking mode. Okay, and the interesting part in this is So in fact, if you call it as MEMS system, so in this MEMS system, my power supply is going to play a major role. In fact, the main advantage of such kind of MEMS systems are, so your power requirement is going to come down. In fact, in that video, you might have seen an accelerometer which is integrated in your vehicle. So where the power generation is very less, the power consumption is very less. So that you can charge it from your car system. Okay. So in fact, to give you a better clarity, so all these MEMS structures are well kept in the form of a single chip. So in this case, two major aspects which you need to look into it. One is your system integration, and the other one is your microfabrication. So your knowledge on microfabrication is more important with respect to MEMS-based structure. In fact, I understand from the schedule, Professor Prasanna Gandhi sir is going to give you a talk on microfabrication. It will be a very nice lecture. He is an expert in that. So a microfabrication facility, microfabrication of MEMS structure. So it is categorized into two different ways. One is bottom-up approach and a top-down approach, where you have wide varieties of windows of MEMS-based building which are available, which is a boom for such a kind of MEMS technology to come. Okay. Now, when we go back with respect to the different system integration, so let me just categorize with respect to the different block. So I have my input. I have my input system, which is available, which is desired measurements or functions. Then we have a MEMS system, which is your okay. We have your sensing or actuation system element. Then we have our transduction element. Okay, and we have a signal conditioning unit. We have a controller, which it can be a programmable base. Then we have the actuator. We have the signal processor. Comparator. Then we have the measurements. So if I try to link it, this is going to be my MEMS system, which is going to be my key system. And when I look into the flow processing, so this is how it is being fed. From this, I am moving to the transduction. From the transduction to the signal. From the signal to the controller. Controller to the actuator. Actuator to the signal processing. Signal processing to the measurement. Measurement to the comparator. Comparator to the controller. Then this is you need to have an output system. Is your measurement. Now, this is your single chip area. So this is your MEMS chip. So in fact, I can just put it up like this. This is a package of single chip. So inside this single chip, so I have the complete micromechatronic systems which is available. And my input signal are well connected to my sensing element as well as to my comparator. Okay, so that's how it is easy because your entire elements are brought down and it made it in the form of a chip. You can easily connect it. Okay, so and then since you have a separate MEMS area where it is your sensing element and then you have your actual element, from the actuator element you are connected to your output or measurement system. So this is, hope now you understand why this is called as your, okay, so I think it should come over here. So this is why this is called as micromechatronic system, because your entire mechatronics element is being scaled down well and it is brought into a single packaging chip so that I can easily interface my input as well as interface my output. So this is what we exactly call it as MEMS or micromechatronics based systems. Okay, so under this micromechatronics based systems, again, you have a micro actuator in place, you have micro sensors in place. Okay, so there are wide varieties of micro actuators which are available. Either it might be in the grippers or it might be in the walls itself. So the interesting part of this MEMS system is basically it's an interdisciplinary system so that you have a different level of engagement from different domain. Even you have quite a good amount of engagement from quantum physics. You have quite a good amount of engagement from solid state physics, from material science, from materials engineering, from chemical engineering as well as electrochemical engineering process. Okay, so I would like to address. So with this, we would like to close the aspects. Okay. So is there any questions? Okay, I think there are some questions which are available. Please type okay. Could you once again focus on building blocks of mechatronic systems? Okay, so don't worry. What I will do is whatever I have prepared, I'll just make it as a PDF and I can share it to Dr. Vasu. So you can just collect it from him. Okay. Respected sir, could you suggest the cutting edge area research on MEMS and which software tool is recommended for MEMS design? See, as far as cutting edge area of MEMS is concerned, in the current scenario, I recommend, according to me, I recommend two areas. One area is your biomems. So with this pandemic environment, so since there is a huge amount of interaction with respect to biomems, so we could able to address different levels. So one example I would say, like your some of these smart watches which are coming. Okay, recently from this BIRAC also, they have approved some projects where they have come up with these smartwatches where you have a small MEMS-based structure which is integrated into it, which will give you a clarity. Nowadays, you don't need to have a thermal imager or something like that. That will give an overall body diagnostics so that you can measure your temperature. It will give you an alarming when your body temperature increase. So it's a very good system. So there we need to emphasize more. Okay. Second area which currently the overall country as well as worldwide are looking into is related to autotronics based MEMS sensors. Okay, because with the current e-vehicle, so there is a need to look into some of the aspects related to sensing. Okay, so that is where exactly these autotronic based sensors are coming into picture. Okay. So in fact, I should say currently India is more focusing towards sensing and sensor applications. So because earlier we used to get many things from China. So now India is more focusing towards sensors. Next is what is the basic difference between sensor and a transducer? Okay, see, sensor in a nutshell, if I would like to say, your LVDT is a sensor. LVDT is a transducer. Thermocouple is a sensor. Okay. The case of LVDT, so it acts as a sensor as well as in some aspects it can act as a transduction element also. Okay, because so when there is the main objective of this transduction element is it converts one form of signal into another. Okay, so in the case of LVDT also, what happens? You have a primary and a secondary coil. Am I not audible?
You are audible only, sir. You are audible. Clear
Okay,
only.
okay. Okay. So you have a primary and the secondary coil. So this primary and the secondary coil moves back and forth. So when this primary and the secondary coil acts as a sensing element, in the vice versa, this also acts as a transducer in translating the appropriate signal. So that is where exactly the transducer plays a major role. So these elements has a sensing capability as well as a translation capability. Any other questions? Some software too. Sorry, I missed. So actually, I understand that there is one session by IntelliSuite. IntelliSuite is a very good software tool for MEMS applications. But we in our laboratory, we are comfortable with COMSOL. Okay, so COMSOL multiphysics is a very good tool because COMSOL has different modules. So based on the different modules, we can easily pick up the domain. So in fact, I work on smart actuators, shared memory alloys, on a macro level also, as well as on a micro level, where there is a heat as well as a structural as well as electrical comes into the picture. So it is easy for me to pick the module and it is easy to work on. So for me, I'm comfortable with console, but IntelliSuite is also a very good software.
Participants, if you have any other questions.
Okay. Anyway, we have another 2.5 hours more to kind of walk around, so we can have some more interactions.
Yeah. So, thank you, sir. Thank you for nice giving introduction, and it is going to be very, very nice, sir. So we will meet back by 2 o'clock.
Yeah, 2 o'clock. Okay. So for smart, for smart actuators. Okay.
Okay. So participants,
only micro.
We will.
I think there is one question from Mr. Ankita. Only micro order chips are used in mechatronics or any other? Okay. See, not exactly. If I try to talk only about MEMS systems, then there is a need to go for micro order chips. Whereas in the case of higher order systems, there is no need to go for micro order chips. Let me just give you an example. So, like in the case of what do you call electrical trains, your monorails, which are available. So in those monorails, MEMS systems are used only in a particular domain, whereas rigid actuators are used. Okay, so there is no requirement. It basically depends upon your domain.
Okay, thank you, participants. As the guest is also there for another afternoon also. So we will be back by 2 o'clock exactly. We will join the session by 2 o'clock. Sir. Thank you, sir. Thank you very much.
Thank you very much. Thank you.
Thank you, sir. The feedback links will be sent in afternoon. Okay. So you please join exactly by 2 o'clock. So exactly we will start at 2 o'clock. Okay. So bye.